Good afternoon, everyone. Welcome to this first joint webinar organized by ANIPH and its sister project, MAGICBIOMAT. I am Cristina Blaya from CETEC, the Technological Center of Footwear and Plastics of the region of Murcia in Spain. And I am very pleased to see such a strong interest in today's session. This webinar marks the beginning of a series of collaborative events between our two projects. ANIPH and MAGICBIOMAT share a common mission to advance innovative solutions and technologies for bio-based, biodegradable materials and products, supporting Europe's transition towards a more sustainable and circular bioeconomy. Today's session is titled Circular by Design, Sustainable Manufacturing of Next Generation Biomaterials. And the focus of this webinar is on how circularity can be embedded into biomaterials from the earliest stage of design. The concept of circular by design means that sustainability is not considered at the end of a product's life cycle, but integrated from the very beginning. It involves aligning feedstock selection, polymer chemistry, manufacturing processes, performance requirements, and end-of-life strategies to ensure that materials can either be safely biodegraded or effectively recovered. With this framework in mind, we will now move to our speakers. During the presentations, feel free to type any questions you have in the chat. We will review and answer them at the end of the session. Also, this webinar is being recorded, so you can access the recording after if you don't be able to stay until the end of the session. So now it is my pleasure to introduce our first speaker, Professor O'Connor from University College Dublin. Professor O'Connor plays a key role in shaping the European bioeconomy strategy and currently chairs the scientific committee of the Bio-based Industries Public-Private Partnership with a budget of around 4 billion euros. He has been at the forefront of bioeconomy development at both national and European levels and has contributed to bringing together industry, academia, and policymakers to strengthen the European bio-based sector. He is also principal investigator on European Union projects, researching synthetic biology and bio-based products. Today, he will explore the production and end-of-life management of bio-based biodegradable materials and the challenges they face within a circular economy that is still largely focused on recycling fossil-based plastic. Professor O'Connor, thank you very much for being here today, and the floor is yours. You are on mute, Kevin.
Okay, sorry about that. I couldn't find the Teams when I was in sharing mode, so I'm going to go back to sharing mode now. I couldn't see the screen. Okay, thanks very much for the introduction, and it's a pleasure to be here. I'm just getting my talk set up. Can you see that now in full screen mode?
No, we are not seeing in presentation mode. Now, yes.
What are you seeing there? Yes? Okay, very good.
Yes.
Great. Okay, so sorry about that delay. Thanks very much. Yeah, my name is Kevin O'Connor. I'm from University College Dublin, and I'm director of a bioeconomy research centre here in Ireland called BioOrbic. We're a national research centre collaborating with industry as well as with other academic institutions. So yes, I'm going to talk to you about bio-based and biodegradable plastics in a circular economy. Just to unashamedly give a plug for a conference that we're organising in September. It's on the International Symposium on Biopolymers. We will look at novel feedstocks, we will look at recycling, metabolic engineering, application of polymers, etc. You're very welcome to Dublin. It will take place on the 6th of September, 6th to the 9th of September. We will have poster sessions for young researchers as well as more established researchers, so really focusing on PhDs and postdocs, and we will have some industry speakers there as well. You can find more information on the web if you look up ISBP 2026. So thanks very much. So what I'm going to do is I'm going to tell you a bit about production of biodegradable plastics, and we're going to focus on a waste resource to produce the biodegradable plastics. I'm going to talk about ReBiocycle, which is a EU-funded project on the recycling of bio-based biodegradable plastics and why we would do that, and also some of the challenges, as was mentioned in the introduction, the challenges that bio-based biodegradables face in a predominantly fossil-based circular economy. And hopefully you see the contradiction in that statement. Okay, so I'm a microbiologist, I'm a biotechnologist, so I like to take bugs, I like to grow them in reactors, and I like to make things. One of the things that we make is polyhydroxyalkanoates, or PHAs. Some of you would be familiar with these. And what we try to do is combine chemistry and biology together in order to transform not just virgin substrates, but also waste substrates into products of value, and in this case, PHAs. So what we do actually is we do a very simple process in hydrolyzing the waste cooking oil, because the waste cooking oil is actually a very large molecule. If you hydrolyze it down to its triglycerides and glycerol, or sorry, from the triglyceride down to glycerol and fatty acids, then the fatty acids are actually much more easy to take up into the cell, and you get much more rapid growth of the microorganism. And so we use this hydrolyzed waste cooking oil. It's a very simple process. They've scaled it in industry, but you can actually do it in the lab as well. It's very, very simple. And what you see in those waste cooking oils is predominantly 18 carbon fatty acids. Some of them are unsaturated, some of them are saturated, depending on where you get your cooking oil. It can vary across the world, but in general, it does contain the C18s with a differing degree of unsaturation. What we did was we basically took a bug called Pseudomonas putida, KT2440. It's a very well-known, well-established bug. And Carolina Ruiz, who did her PhD, she's from Brazil, she did a PhD on the conversion of these waste cooking oils into PHAs and developing processes. So I'm showing one of her figures here, and on the left-hand side of the diagram, sorry, I'll just get my mouse here. We're looking at the cell dry weight, how many grams of cells you're getting per liter inside in your reactor, and also how many grams of biopolymer you're producing. And I have shown two dashed lines here. One of them is for the cell dry weight. We tend to use these as cutoff points. If you don't achieve 100 grams of cell dry weight in your fermenter, then we don't consider it a successful process. We need to achieve at least that, and that's the economics are dictating that. And the other figure is the amount of PHA. So we generally set that at 50 grams per liter of PHA as well. And what we see here is Carolina achieved just shy of 160 grams of cell dry weight in terms of cells, and she just went over the 50, about 55 grams of PHA per liter. These are pretty good yields, and these are pretty good biomasses to achieve in a reactor. So this particular project, for example, would be ready for scale up. In, let's say, 1,000 liter, 3,000 liter. Carolina went to around 30 liter fermentation. So if we look down at the figures, what we see is that we're getting around 160 grams of biomass. Our PHA is around 36% of that biomass is actually PHA, but that equates to around 55 grams of PHA per liter. The yield of biomass is very high, it's around 75%. And basically the productivity in grams per liter per hour is nearly 2. And in effect, you need to be at 2 grams per liter per hour to have a good effective process. So we're there or thereabouts really with respect to the productivity. The yield on PHA is obviously lower than the yield from cells, because you get more cells than you get PHA. So around 30% yield in terms of PHA. In an ideal scenario, you just use waste cooking oil, but the reality is in a biorefinery, you're never going to use just waste cooking oil because you need to have security of supply. There is going to be some inconsistencies in your waste cooking oil depending on what time of the year you get it, from whom you're getting it. And therefore, we looked at blending oleic acid, which is the C18 fatty acid. We blended that at around 70 to 30% of the oleic acid to provide something that would be more realistic in what would happen in a biorefinery. The biomass went slightly down, but the PHA went slightly up. So we had around 150 grams of biomass. We had about 50% of the cell being PHA. And so the yield on biomass went down, but the yield on PHA went up. The overall final PHA production was increased as well. So you're ending up with about 2.4 grams of PHA in a liter every hour of your fermentation. We typically run those fermentations somewhere between 30 to 48 hours, depending on the bug in the process. So if we look at the properties of those PHAs, most people look at PHAs and look at PHB. There's PHBH, there's PHBV. These are basically predominantly 4-carbon monomers inside in the polymer, with some 5-carbon and 6-carbon monomers also included. And the presence of those 5 and 6-carbon monomers is very important in terms of polymer properties. But in our case, actually, what we're producing is a medium chain length PHA, and that medium chain length PHA is very different in its characteristics. And actually, this is there's a typo here. That shouldn't be Chloraphis 555. That should be Putida K22440. It's just another strain we were also studying. And what you see basically is that it has a much higher thermal destruction temperature than PHBs, around 270 degrees. It has a very low glass transition temperature, so it's liquid at room temperature. It's a liquid polymer. It has some crystallinity, but very, very little. It's a pretty much amorphous, and it's actually quite a low molecular weight polymer. So the applications for this are really around adhesives and not as a plastic. When you add the oleic acid, you don't get that much change in properties, really. You get a little bit, you get lower molecular weight, but the thermal destruction temperature and the glass transition temperature are very, very similar. It's, again, a low molecular weight polymer. And so we developed a number of applications for PHAs, including these liquid polymers for hot melt adhesives and for pressure sensitive adhesives. And so we have a number of biopolymer codes, biopolymer 60, 64, and 74. And basically, they are not just PHA on their own. They're blended with other bio-based materials, whether that's waxes, whether that's rosin esters, a variety of different bio-based products to try and create these adhesives. And what we are showing basically is you have fossil-based adhesives and you have these bio-based adhesives, and they're actually quite similar in terms of their peel strength. And then we look at that peel strength would equate to certain applications, for example, in paper labels or cardboard packaging. And we also developed actually a pressure sensitive adhesive. And in that pressure sensitive adhesive, we actually cross-linked the polymer to create greater strength. And that can be used, for example, in removable labels like Post-its or adhesive tape like Scotch tape or sellotape. Okay, I'm going to switch gears now. And I suppose what I'm trying to say to you here is there are ways in which we can make polymers. As a scientist, I'm trying to maximize the productivity of the processes. There are many papers out there that show, and we have papers as well, that show novel feedstocks. You can convert A to B, but the productivity isn't good enough. The volumetric productivity or the productivity isn't good enough. And so I've tried to give you an example here of where we actually have hit very high productivities. And I think that's important if we want to be realistic about PHA production. We have to develop processes that are going to be high productivity. And part of that is the economics. We need to compete with fossil-based plastics. We need to compete with other bio-based materials as well, PHAs do. And so we need to show high productivity. A thing that has come into focus in the last number of years is the limitation or the perception of limitation of bio-based biodegradable plastics, in that they are biodegradable, therefore they're not recyclable. That is the perceived wisdom, which isn't true. And so that's a perception that we need to maybe we need to work on, and we need to provide data to counteract that ideal. What I'm trying to show you here actually is a slide from European plastics and European plastics. So what I'm trying to show you is that effectively on the far left here, we have the total production in millions of tons of plastics, which is around 430 million tons. If you look at the amount that's actually mechanically and chemically recycled, it is about 41 million tons. And then if you go to the far right, if you have the globally the bio-based production, and that's not necessarily biodegradable, they're just the origin is bio-based. We have about 2.6 million, and within that we have bio-attributed plastics, which are plastics that are actually attributed to being bio-based, even though there could be no bio-based material in there. It's just that bioenergy, for example, could be used to make that polymer. I think that's very confusing, and I don't agree with that approach. But you're still, what I'm saying is that basically under 3 million tons of bio-based and bio-attributed plastics are actually produced, which means that there's a tiny percentage of the overall plastics production. And so people look at bio-based and biodegradable plastics as something that is a contaminant, it's a minority, it's not really that important, and actually people don't want it in the recycling scheme. They don't want it in the recycling supply chains. So that's the why and the how. Why do we want to degrade or look at plastics, bio-based, biodegradable plastics recycling, when people think they're not important, they're a very low percentage, but we need to plan for the future. And we also need to get recyclers away from the idea that these bio-based biodegradables, well, they're suitable for composting and nothing else, and they're not suitable for recycling. And I'll get onto another point later about the circular economy and fossil. But for now, another reason why we should be recycling these bio-based biodegradables is that while they're actually performing quite well in managed environments, meaning where we actually industrially compost them or home compost them or anaerobically digest them, there are still a large number of plastics that fail, for example, home composting or fail anaerobic digestion standards. So on the left, I'm actually showing you a variety of different polymers, whether that's polylactic acid, whether that's PHAs, whether that's blends of those polymers, whether it's polycaprolactone, which is a fossil-based but biodegradable plastic, whether they're plastics on their own or blended. What we're saying is if you manage them in an industrial compost, they all meet the standard. If you put them into anaerobic digestion, some of them fail the standard and some of them are quite slow. And if you go into home composting, then you start to see more of them that actually don't meet the ISO or ASTM standards, the international or the American standards. And the picture gets a lot worse if you look at the biodegradability of those materials in the environment. So there is also a perception out there that, well, they're biodegradable, so therefore I can throw them away and they can end up in the environment. The reality is the vast majority of these polymers do not pass the ISO standards or the ASTM standards for biodegradability in the marine environment, in freshwater environment, in like in anaerobic aqueous digestion in terms of at the bottom of a river, and also in soil. So you see a lot of them are failing these standards. That says to us that we cannot have an attitude that we throw these away, but that we actually manage them because they're not suitable for release into the environment. They can be suitable for specific applications. For example, you can design materials to be degradable in the soil and they can be used in agriculture. That's perfectly good, rational thinking. But if you have something designed for packaging and it's not designed for soil degradation and that is released inadvertently or without managing it and it's released into the environment, then you cause problems. And so ReBiocycle came into existence along with two other projects, sister projects, that are also funded by the CBEJU, MyBios and Prosper. And we're effectively trying to do very similar things. We're trying to create circularity in bio-based plastics, and we're particularly focused on bio-based and biodegradable plastics. And we're trying to scale these technologies. So at the end of the project, we want to be at TRL 6 and 7 for these technologies. So it's an innovation action, so it's all about scaling. And we just started in late 24. We're about a year and a bit in, and it will end towards the end of 2028. So just to give you an overview of that project, what we're trying to do is look at the collection and sorting, because that's the very first step. Where you have these plastics that basically make up less than 1% of all plastics that are collected. and we need to be able to sort them out so that we can actually recycle them or give confidence to current recyclers that are recycling fossil-based plastics, that you can actually sort out these plastics like polylactic acid, PHAs, the polyhydroxy alkanoates, and composite materials such as those based on starch, blended with, for example, polyesters, other polyesters. And what we're trying to do is take those plastics, create mixtures, put them through the sorting, see if we can sort them out, look at the efficiency, and then subject them to a variety of different methodologies, whether that's mechanical recycling, where polymer goes back to polymer, chemical recycling, where we go polymer to monomer, but then create a virgin grade polymer, or biological, which is effectively like chemical, but you're using biological entities, whether that's microorganisms or enzymes, but you're going from polymer down to monomer, and again getting a virgin grade polymer back. You can have open or closed loop recycling. The closed loop recycling is where you put in a polymer like polylactic acid and you get back out a polymer like polylactic acid. But you can also have open loop recycling, where you might pull in PLA and get out PHA, because maybe the recycling of the PLA is not good enough grade to do mechanical recycling, or it may not be a good enough grade to do chemical recycling, but you could do biological recycling of it and end up with, for example, PHA rather than PLA. That's just one example. And then what we plan to do is once we have the mechanically, chemically, and biologically recycled materials, we will then test and validate those materials for their performance in terms of in packaging or durable products. Do they meet the specifications of virgin-like materials, or are they below that? And also, what about their biodegradability? Looking at the life cycle, looking at the safe and sustainable by design, techno-economic analysis, and then ultimately we want to produce a white paper in collaboration with the other projects, and to actually educate people and get them to understand what can be done with bio-based biodegradable polymers, in order to show that they are, yes, compostable, but they're also recyclable. There's a lot of low TRL technologies out there, and we want to take those and bring them up to the higher TRL. That's the idea behind the project. And we know that bio-based biodegradable plastics, based on the low TRL results, they are recyclable. They're mechanically recyclable, they're chemically recyclable, and biologically. And while fossil-based materials can also be mechanically recycled, the bonds in these bio-based biodegradables are actually much easier to break. And therefore, while fossil materials can be also chemically recycled, bio-based materials are more open to being degraded down to their monomers. So you can use less energy, for example, maybe a broader range of catalysts to achieve that chemical recycling. So there are advantages to having bio-based biodegradables, and also biological recycling. You can do biological recycling of your bio-based, whereas the fossil-based, for example, they're not prone to anaerobic digestion. And in anaerobic digestion, you can actually produce fatty acids, and from fatty acids, you can make polymers again. So there are advantages to using bio-based biodegradables, because they open up the end-of-life opportunities for society. And the other thing is that people think, oh, composting, that's not part of the circular economy. And I'll show you diagrams later where hopefully I can convince you that it is part of the circular economy. So I'm just going to continue on the perceptions now in the next part of the talk. So I've kind of touched on that biodegradables allow for a throwaway culture. You know, people say, well, it's biodegradable, I can throw it away and nature will take care of it. That is really a bad idea. And just to build on what I was saying earlier about the marine environment, for example, if you look into the details, I go to the far right of the diagram first. If you look at PHB and thermoplastic starch, they both make the grade within error for reaching 90% degradation relative to cellulose in the marine environment, marine pelagic, as in out at sea. And it takes 30 days for thermoplastic starch, and it takes about just under 60 days for PHB. But there are other polymers that don't make the grade. And so, for example, PHO takes around 56, let's say 60 days to reach just under 40% degradation. That's also a PHA. PBS takes 141 days and you get about 20%. PCL, which is actually fossil-based, gets to about 80%, but it takes 196 days. And PLA doesn't show any significant degradation within that time period. And remember, these tests are being carried out at 30 degrees centigrade. The sea is very rarely at 30 degrees centigrade, especially if you're from Ireland or further north. You do not see these types of temperatures in the water. So these are the optimal conditions, and these polymers have been ground down. So it's yeah, it's not really realistic to think that we should be releasing these into the environment. We should actually be trying to manage them, and they're a critical resource as well. We should be thinking about resource efficiency within the circular economy. And because we say we're recycling more, isn't that great? We're doing such a great job. Well, the reality is that if you look again to the far right, our circular plastics share is actually stagnating. In 2018 was around 8%. In 2024 it was 15%. But 2 years ago it was very similar, around 14.4%. So what's happening is that the total share of circular plastics in Europe, for example, is stagnating, while the production of plastics globally is increasing. And Europe's share of production is actually also decreasing. So we are producing more plastic, we're recycling, our recycling rates have actually decreased, and that means we're actually producing more plastic into the environment, about 50 million tons per year of additional plastics production. And considering the recycling rates are in the single digits, you can imagine that that's a lot of plastic that's going into the environment or into landfill. And you can argue, well, not all of that is making it into the environment, because some of it's in buildings, some of it's in longer, more stable products. But the reality is the fossil-based economy and the production of plastics is not decreasing. And our capacity to deal with those materials is not increasing. So we're not improving. And so this, I've put a diagram down there at the bottom where you have fossil oil going through this circular loop, but in reality, it's actually going out into the environment. So it's a bit of a fallacy, to be honest. So the idea that we're capturing plastic is avoiding pollution. Yes, if you look at more developed countries, they are actually consuming more plastics. You look at them at the bottom of the diagram here. The plastic waste generation per capita is actually quite high in these countries, but the actual plastic material pollution is lower in these countries. So you can argue the developed world is doing a great job. We're consuming a lot of plastic, but we're not actually polluting as a result of our activities. But there is something that's missing here, in that the vast majority of countries' solution to plastic waste is incineration. So I give two examples: Japan around 60%, and Switzerland up as high as 90% of the plastics are incinerated. So what does that mean? Yes, you're avoiding plastics going into the environment, which is good. You're not causing soil pollution or marine pollution. You're not doing landfill, which is good. You're saying that you're recycling, but in reality, what you're doing is you're burning. And when you burn, you have fly ash, which is toxic. You have bottom ash, which can have a concentration of heavy metals. You have other contaminants inside in the flue gas. And you're also contributing, for example, to global warming through the production of greenhouse gases. So that is just not a solution. So when we look at these figures here and we think we're doing a good job, it doesn't tell the whole picture. So we need to be better. And I know I'm looking at time, so we say that fossil plastics can be circular. That's a nonsense. And biodegradable plastics right now are not part of the technical cycle, according to, for example, EU policy on plastics. So this is the famous Ellen MacArthur Foundation butterfly diagram, where we see on the left you have the bio-based materials, and they are in, if you look at carefully at the green arrows never enter into the right-hand side of that butterfly diagram. And the right-hand side of the diagram never interacts with the left-hand side of the diagram. And that's not a circular economy then. That is two different economies. One on the left is actually circular and it's bio-based, and the one on the right is actually fossil-based. What you need is for that green arrow to be able to be seen to go into the right-hand side of the diagram, so that you can do the things that are happening on the technical side of the diagram. And I've remade that diagram here. And basically what I'm saying is you need to use renewable resources, renewable energy. go through that cycle of manufacturing, but then think about reuse, think about rethinking your use, sharing, redistributing, refurbishing, recycling. But we have to accept that that is all based at the moment on fossil-based resources. So it's not circular. It is a tangential economy where the linear economy is contributing into a partly circular economy. And so we need to stop the use of fossil-based resources, and we need to switch to bio-based resources. And if you switch to bio-based resources, you now have the opportunity to get those plastics into the circular economy, the technical part, and start to reuse, recycle, refurbish, etc. And then you have the bio-based side, which can be much more than just composting or making biogas, because you can use anaerobic digestion to make fatty acids, to make biochemical feedstocks, and you can start using biomanufacturing like fermentation, but not just fermentation. You can also use chemical synthesis technologies to make polymers, starting from bio-based resources. So we really need to rethink this diagram. I'm actually writing a review article at the moment on this, and hopefully it will be published soon. And I've mentioned those two, anaerobic digestion and biomanufacturing. Okay, I'm just going to skip that. Well, maybe I'll make this point. The other thing that the bioeconomy can give Europe is actually security of supply and competitiveness. A lot of people think bioeconomy costs money. And yes, with any new area, there needs to be investment. The reality is that Europe is decreasing its production of plastics, but increasing its use of plastics. And so if you really want to create a guaranteed supply of materials, then Europe should be producing its own bio-based biodegradable plastics. And that will allow it to be competitive and increasing its share of the global plastics production, but making them bio-based and biodegradable. And I think that's critically important. So in conclusion, we know that there are technologies there, biotechnologies, to manufacture bio-based biodegradable plastics. We know there are recycling technologies which we're working on, whether they're thermochemical processes, whether they're enzymatic processes, whether they are microbial processes. You can use these to manufacture and recycle bio-based biodegradable plastics. Circular economy as it's built right now is based on fossil, which I think is a contradiction in terms. I understand that right now we have a huge amount of plastic waste that is generated, and we need to have solutions for that. I'm not saying we shouldn't do that, but we should be thinking about this as a transition and using our knowledge and transfer that knowledge that we've gained from the fossil so that we can actually use it for bio-based plastics. And biodegradable plastics can be central to the circular economy, because the circular economy is about restoration, regeneration, recyclability, compostability. All of those things are possible with bio-based. They are not possible, not fully possible with fossil-based. And the thing is, policy is lagging behind these things, these ideas. And so policy and standards need to be designed to include recycling technologies for bio-based and biodegradable plastics. If we don't have that, then we're going to have further barriers to entry of these bio-based and biodegradable plastics into the market. And I'll stop there. And I just want to thank our funders, CETBIO, for the ReBiocycle project. Thank all the various people up here on the slides who contributed to the work that I've talked about, and to the various funding agencies, including CETBIO. And thank you very much for your attention. I'm happy to take questions.
Thank you very much, Professor O'Connor, for that insightful presentation. I want to remember to all attendees to feel free to type any question you have regarding the presentation of the speakers. And at the end of the session, we will review it. Now, our next speaker is Dr. Yuanyuan Chen, Principal Investigator at the Polymer Recycling Industrial Sustainability and Manufacturing Research Institute at the Technological University of the Shannon in Ireland. Dr. Chen's research focuses on biopolymer synthesis, modification, processing, recycling, and biodegradation. She leads interdisciplinary projects at the interface of polymer science, bioeconomy, and circular manufacturing. In her presentation, she will introduce a circular by design framework for next generation biomaterials, integrating sustainable feedstocks, advanced polymer engineering, and system level strategies for material recovery and controlled biodegradation. Dr. Chen, please go ahead when you want. The floor is yours.
Thanks, Christina. Can you see my slides? I'm sharing, actually.
Yes, we can see, but not in presentation mode. Now, yes.
Perfect. Thanks very much. So, okay, I have 10 minutes. So I'd like to take this opportunity to introduce the project we're working on in PRISM in Toulouse, Ireland. So PRISM, we are a polymer research center in Ireland. So we're based in the middle of Ireland. We're focused on biopolymer synthesis, polymer processing, all types of processing like injection molding, extrusion, compounding, blow molding, films, etc. So from lab scale to industrial scale. And we also do recycling, degradation, etc. So today's topic is circularity. So when we talk about circularity, there are a few key things we need to consider, like alternative feedstock, reuse, recycle, remanufacture, end of life, and hazardous substance, energy, and carbon, etc. So I like to just briefly introduce the project we are working on related to the circularity. So first of all will be the alternative feedstock. This project we actually converted organic waste, basically it's from garden waste into biopolymer. We modified the biopolymer and make them thermoplastic, suitable for 3D printing, and after that we produced the porous structure suitable to be used in hydroponic system for growing plants, and several plants have been grown successfully. So this project is funded by ESA. And then we also convert seaweed into thermoplastics, and we also made we injection blow molded into bottles. So this is funded by Enterprise Ireland. And okay, and this one we just recently been funded by CETBIO. It's a RIA project, and we try to use the untapped forest residue as the feedstock, fermentation process, etc. So several biopolymers were being produced, but I like to focus that we are developing a valorization tool. So it's a digital tool. We want to figure out what the threshold of the forest residue to be removed, because we want to keep the biodiversity balanced. We want to keep the soil. We want to keep the nutrient back to the soil as well when we actually removing the forest residue. And then reuse, we are involved in this EU project. It's called Booty Pack. And this is industrial scale project. So everything like reuse, collection, logistic, decontamination, reuse, and it's B2B, and everything is the industrial level. And we work with Dunmeat in Ireland, and we have demonstrated a reusable this tray for skin pack beef. And we have demonstrated like a reuse up to 15 cycles. So it's B2B. It's for the out of the factory and back to the factory again. Recycling, we actually work a lot. We actually have a lot of projects in recycling, mainly on mechanical recycling, mechanical chemical recycling, like depolymerization. We use this reactive extrusion machine we have is in the picture here. I just like to point out this project we're working on at the moment. It's called Bio2PE. It's funded by EIC Pathfinder. It's about bio-based and biodegradable polyethylene and polyester. But we have introduced this fluorescent marker into recycled material. This allows us to identify, like, exactly how much recycled material we have in each product. Because at the moment, like for example, PET, like 30% recycle, but it's batch wise, like it's from the manufacturer plant. They do 30% during the recycling process, but we don't know exactly how much in each product. Like it could be or like a validation test. So that's what we are doing at the moment for recycling. And then MAGICBIOMAT is founded by Horizon Europe. This project is about biodegradability. We focus on polyester and acrylics as well. Polyester like PLA, PBAT. We have PBS as well. And so there are several strategies we use to control the biodegradability. First one is to use, compounding with more hydrophilic materials to maybe to increase the biodegradability of PLA. In this case, this published paper, like we introduced 20% of cellulose acetate. That has been significantly increased the biodegradability of PLA. And there's so many other materials. At the moment we're working with the other funded EU project on PHAs. We think introducing PHA into PLA will increase biodegradability of PLA as well. So this is just one way. And the second way, we are introducing the microbial promoting additives. And we start with this commercial material. Biosphere is from America, and it's confidential. They didn't tell us what exactly in there, but we did a GCMS. There's nothing really fancy, and so we're actually developing our own additives. But this paper is under review at the moment. But you can see, like, we introduced some biospheres, and sorry, the biodegradability has been increased. Of the PLA has been increased, but I have to use a lot, at least 5% and then 10%. It's quite expensive, and it's quite a lot, I think. But it's proved the concept. It does increase the biomass of the microorganism, and thus increase the biodegradability of PLA. So that's another strategy. And then another one is about enzyme. So there's a paper about PLA degrading enzyme. So you only use very little of the enzyme, so that can actually increase biodegradability of PLA. You just need to make them, the enzyme to be able to stand the pressure and the temperature during the extrusion process. At the moment, we're working on polyester degrading enzyme, and we're compounding them into our materials. And then another material is acrylics. So, acrylics, we can play chemical structures. We can introduce some other monomer like acid monomer. We can also control the molecular weight. So this is collaborating with the Organic Chemia in Turkey. And then, so we actually introduced the AI into our project because we want to figure out, there's a lot of publications. We want to figure out how we actually can control the biodegradability. And we use two ways. First is about mining the data, the published data, but we find there are too many variables. Like there's a lot of standards. People use different standards. People use different grade of polymer. And if it's soil, different soil as well. There's loads of different variables. So we're using this natural language processing strategy to extract the published results, and we can find a kind of a big trend. It's not very very accurate, because there's a lot of variables, but we can see a big trend. But in the same time, we're actually working on our own results, so we can isolate some parameters to avoid the deviations. We like, for example, the grade of the polymer. under the testing standards and the soil, that means the microorganism. So we can isolate those variables, and with the output, which output is obviously the biodegradability, and with that test result, we actually can go back and do the model. And with the model, we have more accurate results. We be able to predict, let's say, for example, like the, whatever now, maybe it's the enzyme, we have like a 2%, 5%, 10%, and then we have different, for each of them, we have different outputs. And then with that test, we be able to do the model. And then we can go back, say, okay, if something we haven't done, maybe 7.5 loading, we be able to predict what's the biodegradability. So that's what we're doing at the moment with MAGICBIOMAT. So that's it. Thanks.
Thank you very much, Juan, for your presentation. There is in the chat a question for you later to the end of the
Thanks.
session. And now our third speaker is Salvador Garcia from CETBIO, the biotechnology spin-off of CETEC, here in Spain too. Salvador holds a degree in biotechnology and a master's in biotechnology in health and sustainability, and he is currently pursuing his PhD on producing PHAs from waste stream using halophilic microorganisms. In his talk, he will briefly introduce the overall concept of the ANIPH project, but he will mainly focus on the biotechnological routes used to produce PHAs from renewable and waste feedstocks and how these processes are key to building a circular value chain from the very beginning. Salvador,
hello.
the floor is
my
yours.
Screen?
We can see your screen. It's perfect.
Okay. Okay. Hello, everyone. As Cristina said, I'm Salvador Garcia from CETBIO. I'm going to present you an project. But first, let me introduce you CETEC Biotechnology. As Cristina said, we are a spin-off of CETEC. Our mission is the bioproduction of PHA in a sustainable way and also competitive. To achieve this, we valorize wastes and use allophilic microorganisms. We also participate in this other European project as a SPEC, Agro2Circular, Peace and Fantastic. We produce PHBB, which is a subgroup of PHA. This biopolymer is a bio-based plastic which is biodegradable in every ecosystem. To produce it, we use microorganisms. Many microorganisms can accumulate intracellular biopolymers as energy source under unfavorable conditions. Alloplasmate RNA can produce PHBB with any precursor. So, ANIPH project will create a PHA value chain to produce wound dressings and recyclable packaging while being biodegradable. This biodegradation is programmed in the production, formulation, compounding, and conversion states. Also, an AI predictive tool and a digital traceability tool will support this objective. Our projects have 8 partners from Canada and 5 European countries from Belgium, Greece, Italy, Netherlands, and Spain. This is the ANIPH project diagram. What can be seen here is how the wound dressing and the packaging are obtained from waste, PHBB, PHN, probiotic, cellulose, and enzymes. The role of CETBIO in ANIPH is to valorize the yeast brewing and sugar-rich residues. Sorry. To produce PHBB. In the case that is required high hydroxyvalerate content, a precursor is added to the fermentation. We optimize the PHBB production in a 2-liter bioreactor from grow and regime condition to the use of the waste and precursors adding. The advantages of this process are that low sterilization conditions are required, PHBB production without adding any precursor, and waste as feedstock for supplying the carbon and nitrogen source. However, the disadvantage is that at the end we get a salty brine, and if we require high content in hydroxyvalerate, we need a precursor. So here we are again in the diagram, and we have explained the role of CETBIO, and now I'm going to show you the role of PHBB. From waste to the wound dressing, CETBIO produce the rich biomass in PHBB, CETEC extract the PHBB, and University of Granada obtain the wound, perform the 3D printing to obtain the wound dressing. Here we have some of the prototypes, and also I have a little clip. I don't know if you can see it. Here's how they print the wound dressing with the 3D printing. And this is the CETBIO team. Thanks for your information. And if you have any questions, maybe I'll talk a little fast.
Thank you, Salvador, and thank you to the three speakers for their presentations. In the chat, we have a couple of questions, but feel free to type any question you have. The first question, I think, is for Yuan. And the question is, currently there are questions regarding PLA compostability. What is your opinion on its biodegradability and compostability?
Okay, PLA, yeah, I think it's industrial scale. It's industrial compostability. Industrial compostable. If it's outside in the field, in the soil, it's not biodegradable. So I think that gives us the room to improve the biodegradability of PLA.
Okay. Then another question we have is, when you talk about bio-based polymers, what raw material do you use to manufacture them? I think the three speakers can answer this question if you want to do it.
In our case, we use the yeast from the brewing and the sugar-rich residues. We give to the microorganism and then produce the PHBB.
And we can use a wide variety of resources. We've used waste cooking oil, but we can also use sugars, but we prefer to try to focus on wastes. Yeah.
That makes sense.
Actually, Christina, I think like Kevin mentioned, it could be a wide range of the feedstock because that's fermentation process. Like anything can be consumed by the microorganism can be the feedstock. You can use plastic as well as feedstock. But if chemical, that would be more restricted.
Yeah. Okay, thank you. Are there examples of biological recycling being scaled or being integrated into a state-provided recycling infrastructure?
As far as I'm aware, not yet. That's the whole reason behind these projects, is to try and scale them, to give the data and the knowledge so that it can be integrated. I think Italy is probably the closest, but they're really doing more mechanical recycling, but they want to try and now move into the chemical and biological recycling. Yeah.
And do you think are bio-based plastics well commercialized currently?
No, is the short answer. I mean, they make up less than 1% of all plastics produced. So PLA is probably in the hundreds of thousands of tons. And thermoplastic starch is up there as well, maybe a little higher. But PHAs are in the tens of thousands of tons. Yeah, maybe Kaneka in Japan is probably going towards 10,000 tons now. So that's a tiny percentage of the 360 million that we're currently producing that are fossil-based.
Yeah, but I think it's increasing. I
Yeah, it's
agree.
increasing.
Agree what Kevin says. Yeah, I agree. But I think the demand and the production is increasing because and
Yeah.
also I think like Kevin mentioned about recycling, like a few years ago, there's never recycled PLA, but now you can buy recycled PLA, and they're actually the same price as a virgin PLA. So I can see the future. There is a big market for bio-based material.
That sounds promising, Yuan. I hope so. Someone is wondering now, Naomi is wondering if is there a reason why Italy is farther ahead than other countries?
Yeah, policy. The Italians introduced policy on bio-based and bio-based biodegradables, mainly driven by one company called Novamont that are producing starch-based plastics. And it was really the Italian government introduced a policy on plastic bags in the supermarket that had to be biodegradable. And as a result of that, that drove legislation on collecting and recycling of the materials. So the production was the first policy, and then the second and third sets of policies were around recycling. So we're collaborating actually with Novamont on the ReBiocycle project and with the Turin, one of the biggest recycling companies in Turin, and they are separating out bio-based biodegradable plastics deliberately so that they can be recycled. But it's less than 1% of the total plastic. Yeah.
Yeah, maybe I can add a little bit. We're working with the University of Padova in Italy, and they mentioned as well, like they have policies. Like, for example, the agricultural film, after use, they have to collect and recycle them. They can't live in the field. So I think maybe they have, policy more advanced than other places.
Okay. We hope other countries see what Italy have done. Another question is, what actions are needed to foster efficient recycling systems for bioplastics and avoid contamination of conventional recycling streams?
So if I can come in there, it's about sorting. Yeah, you have to have the near infrared technology. So there are a number of companies that have developed sorting machines that are able to identify bio-based and bio-based biodegradable plastics from fossil-based plastics. But the efficiencies of detection at industrial scale still need to be further improved. They're actually quite good, but they will definitely need to be improved. So Tomra and others are manufacturing these sorting machines, which effectively are really operating at incredible speeds and can tell you that this is a PLA, this is a PET, this is a polyethylene, and they can do that very quickly. They make mistakes though. They cannot see everything so quickly. So in the first round, you might get 90% efficiency. So that's how you do it, really.
Okay. Another question related to this is from Selamu. Do we need recycling for bio-based materials? Do you think they can perform after recycling?
Again, that's the project, yeah. The project is asking the question, can they perform after recycling? So what I would say is that fossil-based plastics and bio-based plastics both suffer a deterioration in their performance and their quality after mechanical recycling. It is really the challenge in mechanical recycling, whether it's bio-based or whether it's fossil-based, is to retain those characteristics. And that's a challenge. There are many different solutions that can try to get there. But the chemical recycling will be able to produce a virgin grade material. It will be then other questions such as the cost of doing that, the environmental impact of doing that, because you will have more energy, for example. So it will be, each technology has its own challenges, but the performance of the bio-based materials should be no, they should be, they will have problems with mechanical, should be no worse than the recycled fossil.
Okay, thank you, Professor O'Connor. So as we are coming to the end of the sessions today, of the end of today's sessions, I would like to warmly thank you, our three speakers, for sharing their expertise and perspective, and all of you for joining us and contributing to the discussion. This webinar is just the starting point of our joint ANIPH and MAGICBIOMAT series. So answering another question in the chat, our next session, titled AI Meets Biodegradation, Digital Tools for Smarter Bio-Based Materials, will take place towards the end of April. In that webinar, we will dive deeper into the role of artificial intelligence, predictive modeling, and digital traceability in designing and optimizing next-generation biomaterials. We strongly encourage you to join us again for what promises to be a very forward-looking discussion. And to stay updated about the exact date and future events, we invite you to follow both ANIPH and MAGICBIOMAT on social media, because by connecting with us online, you will also gain access to project updates, publications, videos, and upcoming opportunities for engagement. We also encourage you to subscribe to our newsletters, which will provide regular updates on project results, events, and key developments in the field of bio-based and biodegradable materials. Thank you once again for your participation. We look forward to continuing this conversation with you in the upcoming webinars. And yes, answering the last question in the chat, you will be able to get access to the recording of this webinar. Don't worry. So thank you to you.
Thank you.
Bye.
Thanks. Bye-bye.
Bye.
Bye.
Bye.